So it's a pleasure to be here to tell you a little bit about spin physics and spin doctrine. And then you may be curious by this title, Magnetic Cats. What do I mean by that? Okay. And what do they have to do with artificial intelligence and this circular revolution of the spintronics? So hopefully today you'll have a bit of a notion of what it is. No details will be given, but you can always ask afterwards at any time. So when we start a physics journey, okay, we're physicists, I'm a physicist, you have two choices to either go up or down. Going up tends to be a little sexy, just like the galaxies, the planets. Going up in scale is fascinating. You have lots of exciting things, and you've seen them all in the movies, going from Newton to Einstein. But going down into the quantum world is also just as exciting. And here you also go through a trip that is just as long, but down in scale, and it's very strange, Now you're thinking, because you go down to the millimeters, to the microns, to the DNA structure, to the micro devices, to the atoms themselves that form the materials that are defined by the laws of that Schrödinger told us about. Some of you may be thinking that that's where the cat comes from. It's going to get creepy, and there's going to be a dead cat and a live cat and things like that. I reassure you that no cats will be harmed during this lecture. Okay? It will all be happy cats. Okay? Not a problem. Schrödinger cat is happy and alive. Now, within this quantum world of ours, okay, cats aside, there is one major player, at least the one that you actually actively interact all the time with, and that is the electron. The electron is actually the one responsible for most of the physical properties of the materials that you see. They're depending on the environment of how the atoms are arranged. It is really the electrons that give those properties that you see with all the materials that you interact with. And this electron is a little bit schizophrenic. It has a little bit of a problem. It has two personalities. Okay, one is negative, which is the charge. Okay, but that one is something that we can usually use to manipulate and create these currents. So we can move the electrons through charge currents quite easily. And the other one, it happens to be the spin. And this little magnet that is attached, quantized magnet that is attached to the electron itself, it actually makes them antisocial. It makes them a fermion and things like that. But in this case, this is manipulable by small magnets like a normal magnet, a normal compass, you would actually be able to do. The way it's actually utilized in technology nowadays is actually segregated. Oh, sorry. I should actually mention that in this case, this is actually responsible for the smart technologies that you use. So the smartphone, that makes us a little dumber sometimes, okay, is definitely all electronic devices. Then you actually have the Google that you ask everything about, okay. Then you have this wonderful device, the GPS device, that also requires these electronic-based materials. And then the cloud that unites us all. It is important, I want to remind you, that all of these things start from the lab. Without that first step of thinking about the electron in the quantum world to create these smart materials that make those connections, to make that possible, none of this would happen. So, but, from the lab to the hand, takes about 20 years. But this is something that we can ask me later. Now, all of these things have to do with electron and how are they actually being utilized in the actual technology. And this is what I was about to say before I realized that there was a slide in between, that here you segregate a little bit the use of the two qualities of electron. One of them is charge that is used to process the information through the transistors. The transistor is now 72 years old. Okay. So, it's gone through its phases, But now you have many abilities to actually compute many things, but it's the charge that actually is doing it. And then they want to store information, so a spin doctor that actually matches a little bit. And this is where you have these magnets. In a magnet, most of the electrons, all of the electrons within the material are pointing in a particular direction. It's like everybody on the Earth or on the universe pointing together with their arms in a particular direction. That's equivalent to what a magnet is doing at the atomistic level. And this is what is used to store information from the very beginning to the very end at the moment. Now, the spintronics, this is the circular revolution of spintronics, this is the field that I work on, and this is where we're trying to actually unite and use charge and speed at the same, and spin at the same time, a little bit in conjunction to help each other. Often before it was actually quite separate. The first revolution that has actually impacted your life a lot, very, very directly, it is the one in the information storage. They're trying to also make some headway in the computation part, but in the information storage is something that you personally experience. And you probably do remember that eventually around the 2000s, mid of 2000s, you were buying these hard drives that, oh, I have 300 megabytes, this huge thing, you know, it's so enormous, it's $100. The next year, it was exactly the same size, but it was 10,000 times more capable of putting things in there. Exact same price, actually. Huh? So this actually happened. This is this revolution from ink to spin. So from analog, which analog is books, videos, and I'm contractually obliged to tell you that the first analog is Gutenberg Bible. Since I'm from Mainz, that's what Gutenberg was. And then we go from the digital one to the point that now almost everything is digital into zeros and ones in terms of information that we have in percentages. You still have the books, of course, but there's much more generated in terms of information digital that is stored nowadays. What happened in there was the discovery of a phenomena called giant magnetoresistance by these two gentlemen, Albert Fred and Peter Grunberg, where they put a sandwich of ferromagnet or a magnet, a normal metal, and then a ferromagnet, and ran currents through it and saw that they were very sensitive to the resistance they could measure, and they were able to detect very carefully magnetic fields that way. And these magnetic fields were quite important to actually be capable to create and put in hard drives. This was at the laboratory where you create these films very almost atom by atom. And you know, if you actually came up from the lab and you did these devices, they would cost $100,000 per computer. What also was important to actually connect it to another scientist that made it practical. And this is actually, we all feel, many of us feel that should have been the third person in this Nobel Prize, Stuart Parkin, who actually got the Millennium Prize in 2014. And together with a similar effect called the tunneling magnetoresistance, which is similar but put in an insulator in between, they really created these small hard drives of high density. And this is the marriage of this spin and charge tunneling that we were meeting about, the idea of spintronics. And that's the thing that created the cloud. I want to tell you a little bit of how it works because it's important to how I'm going to talk about these magnetic cats and why we're going in that direction. Hard disks are pretty amazing things. If you actually think about them, they essentially have a read head that is very sensitive, and the sensitivity of it all is to this tunneling magnetoresistance that allows you to detect very small magnetic fields from these domains. The more sensitive you are to these magnetic fields that are created by these magnets pointing in one way and another, the more dense the information you can do. The way it reads it as it flies around, it detects that magnetic field up or down. But mechanically, they're fascinating, amazing things. Still a mechanical thing. This thing is going through about 7,000 revolutions per minute, about 15 micrometers above the disk. If I actually translate it to you, it's like telling you that I'm going to put you, instead of the 15 micrometers, let me say that I put you in a big, powerful jet that you have to fly 1 meter from the ground instead of these 52 micrometers. That means that you would have to fly 1 meter from the ground at 2,000 Mach, 2,000 times the speed of sound, and tell me that every house that you go by, without crashing on anything, the light is on or off. That's what it's doing. Whew, yeah? So when you crash, when you have a memory crash, it really crashes. Boom. Huh? It's a mechanical crash. You know, something went wrong, poof, off you go. Now, what is next? What we want to do here beyond this? This is, of course, what is responsible now for this cloud computing, the density that you actually have, all these data farms. They are just all of these amazing, putting together many of these hard disk drives in particular locations that can store all the information that we're generating all the time. But in reality, this is still segregated. It still takes a long time, even though to you it looks instant. When I send an email for myself. It's like it goes to mind and back. Conversion, it takes only 1 second or 2 seconds, which is, to you it sounds fast, but actually in terms of technology is quite slow, okay, compared to the speed of the electrons themselves, of what you can do. And this is where we want to go into next, instead of this segregation that we have in technology, segregation is bad, you do integration. Okay? And integration is one that is going to be faster and more reliable, because we're going to try to go away from this mechanical way of doing things to do everything electrical, such that there's no degrading parts themselves. And remember, they actually know exactly how long mechanically it lasts. The guarantee of your hard disk drive, it is designed such that it dies exactly a year later when the guarantee is off. Yeah. It's like, why did it happen? It always happens. Yeah. Now, there was actually a gentleman that mentioned here that, oh, I heard about MRAM 10 years ago, a decade ago, and it's true. This was the old one where you actually have these cross systems that they were actually generating this small magnetic field. So a current tends to generate a magnetic field, and you can flip your magnetic systems, your domains that way. But it's not scalable. It's just really it was just used for particular small niche markets. What it's actually now using now today is actually a new phenomenon where you run a current through these sandwiches, the ferromagnets, and then so the silicon spin transfer torque, you create this magnetic random access memory that you can put it together on the chip itself. It's memory on chip, integrating all these things together. Let me tell you a little bit of what that is doing. So what we're actually doing in this system is that you run a current, and one of the ferromagnets is going to polarize, so essentially make all of the electrons point in one particular direction. This is the reference ferromagnet, a big one, that doesn't move. And then depending on whether the current goes forward and backwards, this one will absorb this direction, and they will try to line up with it or anti-align with it. Essentially, it goes a little bit like this. They come along, they point in this direction, then they flip around because they don't want it, but then they give their twist to the other ferromagnet, and they're able to rotate it. Sorry, the move is not the greatest in the world, but essentially, this thing is actually moving a little bit. Okay? And these actual switches, when you actually put in these structures, essentially, you have this ferromagnet below, and you're moving them up and down, and then they're transferring angular momentum from here, or angular momentum means that the twist, the way you actually rotate, or the magnetization is also spin up and down, is what it is, that orientation. But one of the tricks in here, you're going through this, that MTJ means magnetic tunnel junction. I apologize for the nomenclature here. And it's a bit resistive, meaning that you've experienced that if you actually have a top, that is to heat up the top, it's a resistive metal top, and then it gets hot because it's resistive, kind of like your laptop as well gets hot, yeah, things like that. So the problem in these memory devices, they're very good, they scale very much down, they're all electrical, but sometimes the actual writing voltage that you need to actually switch this down up and down, and the breakdown voltage, the meltdown voltage, come together. So instead of a crash, you have a meltdown. Okay, so the next memory devices that you're going to have, instead of this memory crash, is going to be a memory meltdown, something that sometimes is familiar. Now, on the other hand, that is a challenge. Nowadays, these are actually commercial. It's just become to be commercial by Toshiba. There's ways around to making this more reliable, and it speeds up the computation. So you're making things faster. Okay, that much faster in terms of this communication. But what is that? But that is the problem. The minute that you're using charge, the minute that you're actually using charge currents, you're never going to get away from the heat. It gets hot. Okay? Now, what could we use to something that we can transfer information from one place to another and not use so much heat? What do you think? Light. Could be. But light is actually something that I have in mind a little bit. But say, for example, I ask you to do something, to go there and tell this gentleman on the other side to stand up. And to do so, you have to get up and go, yeah? Right? And then move around and make collisions and heat and disturbances, yeah? But there's another way to communicate that, right? How do we do it? You've seen it before. Actually, it's probably happening in the World Series game at the moment. Yeah? The wave. Can we make a wave? Wave. No way. Doesn't work that way. Okay, so if you make a wave, you're able to actually, without moving around, transport energy, transport information. Okay? Without a lot of cost. Now, what type of waves can we do? And this is where Spintronics comes in. We want to create what is called spin waves, the spin currents. Okay? And this is where Einstein and Dirac come together. This is They mentioned that the charge and the spin are decoupled, that they don't talk to each other, but that's not quite true. It actually, when you put quantum mechanics and the special relativity of Einstein, that gives you the Dirac equation. And this is the connection, the phone line that you actually have between the charge and the spin. That's the thing that connects the two and gives us some effects that with that we can generate a spin currents that we can utilize to flip things around. One of these effects that arises from this thing, this is what I'm here primarily for those successful in science, is the spin Hall effect, which is, you can think of it as a spin wave battery, where you run a current in particular material, and because of this coupling between the spin and the charge, this is spin orbit coupling, you're able to generate a spin current perpendicular to the current, okay, that you can actually transfer to other places. It's actually important for Santa Barbara as well. It's actually something that occurred here. This is a prediction long ago about the extrinsic one that has to do with deflection from impurities. You see an impurity, an electron goes left and right, and therefore the spin ups go one side, the spin downs go to the other side. Or another one that is the intrinsic one, which is more dominating than the one that is used in technology. But this one was an important discovery that actually was first observed here in Santa Barbara by David Ashelom's team, okay, who was formerly there at the time. Now, you have a spin generator, so you're able to generate this spin current, okay, which is a twist current, essentially a flow current that it goes from one side to the other by this spin Hall effect. How it works, don't worry about it. It's just, there's some more exoteric details. But this actual spin Hall effect, there's more to it than you can meet the eye. Because studying this thing, it actually helped us to actually discover new type of materials. So if you actually do the spin Hall effect with a very, very strong connection, you end up with things what is called topological insulators that you may have heard about some talks here in the past. Then you can create a spin Hall effect transistor, which is totally useless, okay, because the input to output is 1 to 1,000, so you're not going to use it, okay. But what it became very, very useful, and this is what now is actually now in prototypes in many devices, is to make MRAMs that don't melt. And I'm getting closer to the cat. Okay, I know the cat people, but there's some dog people. Is there dog people here? Okay, I haven't made a magnetic dog yet. Okay, except the dog hair clinches to everything like a magnet, but that's a different story. Okay, so how does this work? A little bit. So essentially, the idea is that instead of running a current through this resistor part, this is metal tunnel junction, you run the current in the other side on the top, because this line in here is a very nice metal. A very good metal with a current doesn't heat up. The thing that heats up is when you have a resistive metal with a large resistor. Okay? So if you're able to run the current in there and flip your ferromagnet below by the direction of the current, you don't have this meltdown problem, yeah, anymore. And this is what happened now about 8 years ago with 2 experiments that showed that you could actually generate these things, one by spin Hall effect. Essentially, you run a current here, and there's a spin current flowing into the ferromagnet that flips it. But there was another one that had another interpretation, which had to do with another, and this is unfortunately, the name is not so sexy. It's called inverse Bill-Galvanic effect. Say 3 times, inverse Bill-Galvanic effect, inverse Bill-Galvanic effect, inverse Bill-Galvanic. It rhymes after a while, yeah, after a while. The first one is, as I mentioned, the spin Hall effect, that you generate this spin current, essentially spin ups go out, spin down. So, and then this is a flow, and then this makes the ferromagnet switch, okay? The other one is a little bit that you create internally from this coupling between the spin and the charge an internal field proportional to the current that is able to switch you, okay? So these are magnets or magnetic devices. They have a magnet together with another metal that are switching themselves. You're beginning to see the cat analogy there. Huh? The next step on that is that here you had devices where you always needed a partner to give you that spin current, that generator spin current. And in here it was very difficult to distinguish it was this one or this one coming up, because by symmetry, by the experiments, you couldn't really take them apart. Instead, what we actually did is to create a ferromagnet that itself doesn't have a really spin Hall effect, it just has this inverse Bill-Galvanic effect, okay? We call it Joe for now, okay, the Joe effect. And then they were able to switch itself just by running a current through it due to this coupling between the spin and the charge that we have given to us by Einstein and Schrödinger coming together. In doing so, what you've achieved is to behave in something like a cat. Now, cats have a wonderful ability. Okay? You're not supposed to do this, I'm told. But if we were young and naive, you may have taken your cat and put him in its bag and drop him, her in this case. And there was no problem, no harm, because it was able to twist itself to where one part of its body will twist and the other one will twist until they see the floor and then land on their feet all the time. This is the idea that here this ferromagnet is generating through the current, through this effect of coming from Einstein and Schrödinger, giving us Dirac, that was able to generate some twist that flips itself alone, without any moving parts, with anybody helping him. It just does it by itself. So we've created a ferromagnetic cat. And we've actually solved the problem of melting. So you don't have any meltdown on your magnetic RAMs, access memories anymore. So this is the cat. I'm getting to parts of the titles at some point. Now, what is next? So it's very nice because it actually makes things very fast because it's all electrical. It generates very quickly, and poof, you got magnetic random access memory. Even though I can assure you for 100% that when we were studying this, that was not our motivation. As scientists, we're motivated by the fascination of these physical effects. But it turns out that it's been practical, which is always a good thing. So one problem is solved. We're faster, okay? But what is next? So you have this motto, Olympic motto, yeah? Faster, higher, stronger. You see, we also have this other Tech Olympics. And there's a different motto. And the motto is faster, higher efficiency, stronger connectivity. Okay? It's not a real motto, really. I just made it up. But anyway, we'll go along with that. Okay? So faster we've achieved. But what is happening with the other two? Why do we need it? Because this is actually societal challenges. These are the grand challenges that we have. If we don't solve them, we have a problem. A big problem. It's beyond the other problems that we have now in this country. Well, I'll mention that at the end as well. I'm on the other side of the continent now. So, the higher efficiency. Why do we need higher efficiency? You may feel guilty now, and you probably will try to Google this information, okay, of the fact that every 30 Google searches boils a liter of water. Oh, yeah. Google away. Yeah. You should be more conservative when you're Googling. Yeah? Okay. You want a tea? Yeah, go for that. There's 3.5 billion per day. That's probably obsolete now because that was last year. Okay. But now it's 7% of the electricity generated in the world is actually spent on these data farms. By Google, by Amazon, by all the YouTubers in the world. You know, don't remember that you used to have dial-up, yeah? Try YouTube with dial-up. Cannot forget, eh? Yeah. Now, 7% is now used, and it increases exponentially because we're insatiable in terms of the data that we like to consume all the time. So it is a bit of a problem, right? The 7% was not there before 5 years ago. Now it's 7%, and it's going to get bigger. Okay, so that's more efficiency of how we actually deal with data, transfer data. This is the largest problem. It's not the computation. The computers are good, efficient, not a problem. It's really the retrieving and reading and storing of data and information that is really the culprit for most of the consumption of electricity, in this case in technology. So that's the problem we need to solve, yeah? And then the stronger connectivity. This is something that you may not be aware, but you may actually, a little bit, that you have this called this terahertz communication gap. Electronics, they're here. They're actually pretty fast. They're not so bad, yeah? But a little bit slow compared to the optical fiber networks that actually connect us. As you mentioned very correctly, to communicate fast distances is much better to use light. But in between the two, you see, electronics goes up to gigahertz, which is a frequency that is not light. And then once you get to terahertz, this is when you get to light. But in between the two, between 0.3 and 3 terahertz, there's a vacuum. There's this Figgity bridge in there. Yeah? You have to slow things down, go through the bridge, and then you go to the electronics. So it's not very good. You have this gap, this bridge gap, that you need to try to have a material that could maybe put you together in both of them. So what you need is materials that are more efficient, that connect you better. I don't know what happened with the, oh, sorry, I didn't mean to do blue. There's nothing specific about the blue here. Okay, it's not on net, it's connect, yeah? And I still do it quickly. And this is a bit of the idea of going back to analog, okay? And what material could that be? So I'm going to tell you some materials that we've been working on the last 5 years or so. And these antiferromagnets. Ferromagnet, because I talk about magnets, but both ferromagnets and antiferromagnets are magnets. Okay, we're all very inclusive here, you know, integration. Ferromagnets is where all of the electrons are pointed in the same way. Antiferromagnets does not mean that you are against the ferromagnets, yeah? You know, it doesn't mean that you don't like ferromagnets. It's actually a poster from one of my centers, you know. So as you can see, we have a little fun with these things, yeah, all the time. It's actually materials where the spins themselves are very aligned as well, but one of them in one atom is in one direction, one in the other. So they're compensating each other a little bit. If you put magnets that compensate each other, they have some interesting abilities and some characteristics. In technology at the moment, we're using ferromagnets, but there's not so many of them. Each of you are paying $10 a year, $15 now by now, I think, in about 4 materials that are actually used as ferromagnets. Antiferromagnets, there's more of them, but they have the ability that, a very specific ability, they're insensitive to magnetic fields. And why they're insensitive to magnetic fields, that also makes them hard to manipulate. That was always the challenge. Because you have all of these materials with these very beautiful properties, a property that they're faster. The actual ferromagnets, they tend to be gigahertz. The natural speed of how they rotate are gigahertz in the terms of electronics. The antiferromagnets can go from gigahertz to terahertz. So if you can use them and you can talk to them, that would be a cool, cool thing. But the problem is that with the read heads, you cannot, because you need like 100 Tesla magnet to actually flip these things around. And if you've seen 100 Tesla magnet, do not bring any credit card next to it. Unless you go for a shopping spree and you don't want to spend too much money. Then it's okay. Bring it along, okay? Now, they also, and this is a connection with artificial intelligence, they have this behavior that they behave a bit like synapses and neurons in terms of the kicks and the loss of memory that I'll show you in a minute. And this is where the analog comes in, okay? Now, what happened is that about also 5 years ago, happened nicely when I was moving to Mainz. We were working on the systems and we decided, can we actually make antiferromagnetic cats? And by that I not mean a dog, yeah? I mean an antiferromagnetic cat using this material and then that it can flip around through the current just like we did with a ferromagnet. And the idea is a little bit like this, that you actually have a material that you can think of it when you actually make a coil in a current, you generate a magnetic field. And in here, the coils go in one direction, in one orientation from some of the atoms, and they go in a different orientation, clockwise or counterclockwise in the other. And it has to do, of course, it doesn't quite look like that, yeah, but it is a bit of what is happening, that you're able to run a current through this specific material where the atoms are arranged in a specific way with that connection between the spin and the charge, and generates opposite polarization in opposite lattices and opposite points where the magnets are. And that way, depending on the direction of your current, you're able to manipulate it. So for the first time, you were actually able to actually switch a antiferromagnet electrically. Now this is I'm very proud of, because in this field of mine, it is virtually impossible to predict something that not a Russian physicist had not predicted long ago. That they didn't get. So, yeah, because it was a crazy idea. Yeah, it's totally crazy, you know, how you're going to make an antiferromagnetic cut. But the nice thing about it that we have colleagues that they actually had the material nearby, so you actually put this together. This is a little box like this, sorry. If you can actually see, the magnet is switching around when I turn on the current, you know, these little magnets are flipping around, you see? Unfortunately, the arrows are a little small, huh? But it works a little bit like that. And they were able to observe it less than a year later. Within a few months, they had the material, and they were able to switch just by running a current up and down. This is, I think, the first data that I show you, it just goes up and down, depending on the pulses. Okay, and you can measure it. It's an electrical measurement that you can actually measure and see that it's actually switching. Okay, and there's other means to tell you that the antiferromagnet is switching, not just the material changing or anything like that. Okay, so this is some data that I will show you. But it was from there to actually possibly making a device. So there is not that many occasions when you actually go and do a prediction of completely new thing that a Russian has not predicted before. Okay? To actually discover the thing, I'm a theorist, so we're very proud of predicting things because experimentalists want us to prove us always wrong. It's like, you were wrong. Say, well, this time I was right. Yeah? And then they actually observe it, and then they put it in a device. It works in the Macs. I'm not sure if it works in the PCs, but definitely works in the Macs. And this, by the way, ladies and gentlemen, I want you to remember today. Today is October the 30th, 2019. You're seeing the first antiferromagnetic RAM in history. MRAM, okay? Antiferromagnetic NRAM in history. It's not like antimatter or anything like that. I'm pretty sure, not 100% sure, but I'm pretty sure that you will talk to your grandchildren about it when they're having these iPads with antiferromagnetic memories. I saw that in the KITP the first time. Please remember that. And give KITP a little credit, huh? Good. So now, not only that, this thing, of course, is done electrically. It just goes into the laptop. It's just put into a chip. It does electrically. But then we were able to tell. Remember that I told you that these guys were able to actually operate at the terahertz. At the gigahertz, there's nothing electronically that you can actually do at the terahertz. You can create an antenna, and then it propagates, and it's terahertz. But electrically, it goes up to the gigahertz, and you stop. Now, you can do the experiments doing the currents, or you can shine a light pulse that is also like an electric field wave. That light shines into the device and see if you are able to pulse it and do it fast. So here's the experiment. I'm sorry to show you. It's just to demonstrate to you that here the difference between this experiment and this experiment, they look the same to you, right? I swear to you, I did not copy and paste. Huh? You can see that they're different, okay? If you look at the wiggles, they're definitely different wiggles, okay? Hopefully. Yeah, they are. Okay. They're different wiggles. Not only that, one of them is 1,000 times faster than the other. Okay? What is the difference in here is that the pulses themselves, it actually, one is megahertz, one is terahertz. And they're behaving the same. And, just going a little bit towards the artificial intelligence, what is happening, you're sending pulses, so you're kicking and kicking, and the device is changing and changing. So just remember every pulse you're giving it. The synapses in your brain remember pulses, as long as you don't forget too long. And there's a little bit of forgetfulness once you stop the pulses. So this is where these devices tend to behave a little bit more like neurons and synapses that can come together. But happily, with this, you've demonstrated that you can actually bridge the communication gap with the Golden Gate Bridge. Okay? Looks very pretty. Just did that today. So now you're happy, faster, higher efficiency, stronger connectivity. Let me remind you, and feel guilty about your Google searches. What about the efficiency? And this is where I'm, up to this point, it was all science, demonstrated, and now I'm going to leap a little bit. But not too far, because, we actually, it's a little bit scary, but I wanted to excite your imagination a little bit. So we actually are in the midst of a revolution, an artificial intelligence revolution. But in this case, it's a digital one, okay? A digital computer, you have the AI computers with GPUs, TPUs, whatever. I don't know what TPU means, but TPU I do. But to actually process, our brains are amazing things. We are epiphany of efficiency, okay? Just the same computation of recognizing things and logical things, it takes 100,000 watts in here, doing it with zeros and ones, mimicking what the brain does, and 20 watts in there. Right? It's pretty cool. Huh? It has to be cool. That's why it's 20 watts. Yeah. Otherwise, each of you is 100 watts altogether. So it's like 100. That's why things get warm in a room. It's like 100 watt bulb each of you emanating. Yeah. But only 20 watts is for your brain. Okay. Now you have 10 to the 11 neurons. and 10 to the 11 synapses, which are the connection between the neurons. That means about 100,000 to 10,000 connections between each of the synapses. A normal computer has 3 connections, yeah? So it's a bit more parallel than the other one. But extremely efficient. Let me tell you a little bit more about the differences between how a normal classical computer works and a brain. Okay? The classical one works at gigahertz, except for now the antiferromagnetic one, which is going to be terahertz, but okay. That's still gigahertz, okay? We are very slow. We're kilohertz, 1,000 of a second. Actually, if you actually react, you know, the sprinters, when they react almost instantaneously to the gun, but faster than 1,000th of a second, that is a false start, because your brains cannot react faster. You actually, synapses is actually utilizing ionic currents that are actually moving, and they cannot physically do it faster. Okay? One is digital, meaning zeros and ones, and one is analog. Analog, you know, if 0 and 1 is exact, the analog is like maybe. Okay? That's analog, kind of in between. Huh? Then you have, one is rigid, you know, it's the architecture is there, and our brains are a little bit disordered. And you feel that sometimes without the coffee, you know, it's a little more like that. It has to do with that. Also, this, it has a clock, a particular clock that it follows one to the other one, very rhythmic, very, very Germanic, yeah, almost. I'm in Germany. Ich bin Deutsche jetzt. Jawohl. Sorry. This is taped. Okay. And then, but the other one is asynchronous, meaning that in your brain things fire back and forth without you knowing. And one is sequential, meaning that goes from, you know, one to the other, passing the information. Can do some parts parallel, but for the most part sequential. And the ours is massively parallel, but really, really massively parallel, because of all these connections that we have. One is in-memory computing, so one has integration, which is what we're trying to do. One has segregation on the von Neumann architecture. One is not redundant. Essentially, your computer breaks down, that's it, get another one. In ours, our brain stays with us the whole lifetime, but it can repair itself very often. So this is all because of these redundancies that we have. You don't have one memory, you have many memories all linked together most of the time. And one is good for very well-defined things, and one is good for ill-posed logical things. I still want you to understand, though, that this, within the architectures, there are different types. There's different types of computers, and there's different types of brains. Okay? Some of them are good for simple words. Another ones use whole phrases, and another ones use 128 characters. I won't say which one, but, you know, they can give you lots of brains and stable geniuses. Now, on the other hand, you got to remember that you're losing 10 to the 5 neurons per day. Scary. Today you lost it. We get dumber and dumber every day. Everybody's calculating, you know, how many do I have left? You have 10 to the 11 to begin with. Yeah? 10 to the 5, 100,000, you're gone. Yeah? Don't worry too much. By the time you die, it's only 2.5% that you lost. So you do get dumber, but not that much. Okay? Well, some people seem to have more left than others. Okay. I'm not saying names, yeah? It's okay. So, but the nice thing is that this all comes, this machine learning, it actually is arising from these studies of utilizing these deep neural networks, which is actually something that was a study in a different field of physics, spin glasses, disorder systems, where they actually, this hierarchy that you're actually given a synapses, and then it cascades down and gives a signal, and what happens in between you don't quite know. The interesting thing, and you may have noticed yourself, 5 years ago, and actually I did notice a lot, because I moved to Germany, and I was trying to use Google Translator, because I moved to Germany without knowing any German. Yeah? Sehr mutig, yeah? Sehr mutig. That means very brave, yeah, in German. Don't worry, I did this before when I moved here. I was actually 16 years old and a high school exchange student. I decided to stay after that for 25 years exchange student. I don't know who else went to Spain for that. But at the time I didn't know English either. So I thought I would make it work with the, but the point that I'm trying to make is that you try to use Google at the time, and the translation were funny. You know, you do it once or twice, these translations really look funny, because they were trying to follow rules, instead of pattern recognition, that is actually what is utilized nowadays. And now it's pretty good. If you really want a very good translator, you can use Google, or you can use deepl.com, for example. Deeplearning.com, deepl.com is a fantastic tool. Huh? But they're using all the same trick. Essentially, they're using all these tricks of these neural networks, of different versions of it, and I'm not an expert on it, so unfortunately you can ask me about it and I'll just tell you my naive understanding of it. But for picture recognition, this actually has changed in global entry now. Instead of the fingerprints, you know, just look at your picture, it's like, ah, hello, Jairo. It's like, okay, that's scary. And then audio transcribing, the same thing, you know. Text translation, gameplay, fluid dynamics, all use the same trick. It actually is funny because, you know, these Google things, you know, you have to think, you know, what are you being utilized all the time nowadays? You know, again, they're digital, they're still fast, and I would like to tell you something. A little story that a colleague of mine told me that is quite funny. I forgot it was Google or Amazon or whatever. They actually implemented this algorithm, deep learning algorithm, to actually use it to answer the frequently asked questions from customers, and the emails will sound like a human had written them. Turn it on, it starts working. Ah, it works perfect. We're going to have coffee. We don't have to answer the phones anymore. Wonderful. They were having mostly coffee meetings all the time for about 3 weeks. Then all of a sudden, they get a flood of emails complaining. What are you doing? What are you saying? How are you so rude back to me? You know, I mean, how do you treat your customers? You see, it's a pattern recognition. It recognizes and learns the patterns. It learns from the customers how to answer them back. And then these managers come and go, what's happening? What's happening to the scientists? And they're like, okay, I don't know. It just works. Because these neural networks, because of this dimensionality that it has, we know that they're working. We know a bit about it. But a bit on the scary side is that we don't quite know how they work. They just work. A bit like our brains. You don't know how it works. They just work, yeah? And, you know, so they say, oh, no problem. I can turn it off. So because it's still, you know, running not so fast, you can turn it off. Put a little bit of settings, you know, filters, back on. And then you also have to adjust it. The idea is that you can turn it off, okay? Because it's kind of isolated. It's only receiving emails. It's not connected to many things. Now, this deep learning and all these things are developing pretty fast. Let me give you an example. These are famous people. Don't look like famous people? They look like they're in a catwalk or Hollywood or something like that. Pretty good, huh? I mean, definitely she looks like she just came out of the salon. He looks like he's going to a party. This person looks like he had too many drugs in the 60s. Right? All of these are actually generated by a computer from a random number, and they are fake people. They don't exist. They never existed. They just gave a number to the computer. It learned how famous people look like. And from that, a number, I don't know what number will be your number, but for the famous people, we kind of assign some numbers, and you get these deep fakes, they're called now. It's not fake news, it's deep fakes. Huh? So it's a challenge, you know. The same thing with this other thing. So, but what I'm trying to say that in this case, this is still digital. It'll still consuming lots of power, and it's still not so fast. But here comes this notion of trying to be more efficient and faster and connected. Now we have these materials that can be utilized to create these these neuron-like hardware devices, analog devices, okay? That means that they will be faster by themselves. They will tend to be more parallelized, and they're also connecting to the Internet of Things because they've bridged terahertz cap, so they'll be able to connect to all the devices. Now, if you manage to actually create such a brain, it's a big if, you know, but remember, the transistor is 72 years old, the Internet is 36 years old, and the cloud is less than 8 years old. Okay? So if you tell me, oh, that's not going to happen in my lifetime, okay, in your kid's lifetime, it will. So, we speed at kilohertz. This sucker is terahertz. If you do the calculation, that means within 2 minutes, this brain will have learned the entire history of humanity and not forgotten it. And it will decide what it will do with you. A bit like the Terminator, yeah, the deep sky thing, yeah. But, you don't have time after 2 minutes to say, oh, I'll just turn it off. No. Hands off. So this is the end of it, essentially, where the revolution, that it always continues scientifically. But what is important to understand is now scientifically, and I was actually doing my center as well, is an interdisciplinary to connect things, that we don't only just talk to scientists. We need to also be discussing about when do we go from face recognition to this technology that we are creating to creating a culture, to creating these biases. Where is that going? Because we as a society, we're very slow. We've evolved amazingly, but we've evolved slowly through millennia and millions of years. Yeah, to be extremely efficient. We don't quite know how it is, but our technology typically outpaces us. We do terrible things with the technology we get until we adjust. But we are telling, in this case, this is a big deal. It can solve our grand challenges, but we need to know where it goes. So this is one thing that I leave you with, that essentially you have now this revolution that you've gone all digital. Likely in the next future, we have to become to be more analog in the meaning that you create these infrastructures to create these magnetic cards. I found that in the web at the last minute. It was very cute, yeah? A little magnet. And then connecting these things. Now, all of these things may or may not work at the end, So what do you do if it does not work out? And this is why I love being here in Santa Barbara. Because I always have a universal solution. My universal solution, if things don't work out, have some wine. So thank you very much for your time. Anyway, if somebody asks me, am I happy in mines? That's my cellar.
Okay.
Yeah, life is good.
When you're talking about the heat and the electricity consumption, since, as Lars knows, one of the top people in the world in photonics is only a couple hundred yards from here, have you had a chance to interact at all on your work with Dr. John Bowers?
Yeah, so I know John, but we have not really worked in the same field. So in this particular case, he goes at a different frequency range, not the terahertz, but no, I haven't. I mean, the nice thing with KITP is that it brings so many people together, and it also addresses these interdisciplinary ideas that brings two workshops that have different connections, but try to make more and more connections, not just astrophysicists with physicists. But unfortunately not. No, I haven't. I'm drinking all this wine. I have no time.
So another question.
Yeah, it's a little bit too much. Huh? Yeah?
Yeah. Mark's going behind you.
Could you speak a little bit more about the commercial applications that are coming on the market? I think I heard you say Toshiba.
Yeah, so the magnetic random access memories, they used to be by a different company here in the US, Everspin, it was called. But they were more for particularly military-oriented devices. Now there's actually Toshiba, I believe they're now putting in the market this MRAM of about 1 gigabyte that goes on chip. So it's on chip memory. And where this is going to go, I don't think they're going to replace immediately your farms where the disks are, because in reality you have still the cost is what also matters commercially at the end of the day. Many things, oh, it's beautiful, it's wonderful, but it's $1,000. It's like, okay, no, I'm not going to work for that. So that's one thing that we scientists don't know about all the time. But in this case, Toshiba now, I believe they actually have now commercialized them now for the 1 gigabyte type of memories, but they will be more specific towards laptops and things like that to make them cooler and more efficient at the laptop level, at the personal computer level. You also have, by the way, a large fraction of data now is still on tape, not on hard disks, because tape itself is one of the cheapest to actually do. So for the long storing of data, you still have magnetic tape. It's still kicking around, go. You know, for the old guys that like the, you know, you miss the diskettes, yeah, and they're still around. Yeah, so. Yeah, and by the way, this antiferromagnetic stuff, in terms of the workshops that we organize, it's been tremendous over the last 5 years, going a bit crazy, to the point that in most workshops, we always just see scientists. But now every workshop, there's a guy from Intel coming along, and a guy from all these companies with piquing interest, because nowadays, Moore's law is, you know, it didn't die, it melted. Yeah? Essentially, this idea that your laptops go faster and faster, they look pretty and pretty, and the cost goes higher and higher. That's about it. And they are just desperate to know what is next in terms of, and this is where it's coming a little closer now to basic science.
Does this have direct impact on the 5G type of advances?
No, I don't think so, because the 5G itself is more of a network infrastructure that you're actually building. That is actually non-technology, not the next one. I remember that these things, at the end of the day, Moore's law was a business plan, yeah, to do it. The 5G, I think, is more of a structural one, not connected to that. I may be wrong, by the way. This is my impression. Yeah.
So is anybody looking at the biological impact of the magnetic field? I mean, there's been a lot of talk about the old architecture and
right.
How
So magnetic fields themselves, they don't tend to be too harmful. It's the currents themselves, the electric fields, that are harmful. In this case, particularly antiferromagnets, you could digest all the antiferromagnets you like. They don't create magnetic fields. They don't create fringing fields like a magnet. So those, in that sense, biologically, from the safety point of view, is amazing. Of course, if you make them from bad materials that are toxic, that's a different story altogether. Okay? So this chemistry gets in the way sometimes. But from that point of view of those magnetic fields, antiferromagnetic materials that we're discussing to go faster, they're very exciting from that purpose. It also makes them harder to activate, and this is why this breakthrough 4 or 5 years ago was such a big deal for the community. But in itself, that actually is an advantage. You still have the currents that you have to actually have in the devices, but it's still a pretty good aspect in the biological aspect in terms of being able to put them together. And I hinted to that. With a ferromagnets, there's not that many of them. You know, most of the materials themselves, when they magnetically order, they tend to be antiferromagnetically ordered, because it's a precursor as well to a thing called superconductivity, which many things call superconducting when they're cool enough. And then that also gives us the ability to explore more materials, to say, okay, if this doesn't work, this one may work, and it's better. So that's actually a nice playground as well.
What kind of metals are you talking about?
So this is copper manganese arsenide. It's one of the ones that we had. Copper is all over the place. It's okay. This is just abundant materials. We're not talking about rare earths or anything. So China will have to be involved, you know, except to help Trump to find something about the Bidens. Sorry.
So Jairo, let's imagine in 10 years you come back and we ask you to give a second public lecture, which we never do.
Good.
Because
good.
we're not,
No, because then you have to be like, well, you said that. It's like, oh.
But the question is, what would to you be the vision of some impact on technology that you could imagine happening?
On these things that we're discussing, right? What I would like to see here much more is, what I would find exciting is we begin to have more Renaissance science. And this is actually connected to Humboldt. You know, actually I got to know, I think Mark says that I'm a humble professor. I'm definitely not humble at all. Okay, I'm a Humboldt professor, as you can imagine. Now, in this case, you know, Humboldt believes a lot into the interconnection between sciences. Because nowadays we're still working very much on, I'm going to make this effect, and this effect I'm not going to worry what it's going to do. And he will do something. And in this case, I'm beginning to see sciences where are connecting more anthropology of how to actually make this impact of these technologies, which mathematically, how do you mathematically put culture? How do you actually model that or even think about it? But for that, you need to talk not to the scientist that is next to me, but to the anthropologist that is next to me. And that type of science, more Renaissance, you know, because Humboldt try to actually learn all of the science by the age of 45. You know, this is, you know, it's too late for me. I was trying to do that, but it's not going to work. But at least to do that. So I think I would like to see much more scientifically more connecting between the sciences, with different sciences, the ones that are actually connected to impactful things.
Okay, thank you. So we still have refreshments for those who didn't get them before or once more, and otherwise we'll see you at the next event. Thank you very much.